So let's start this lecture. It's open mapping theorem. Open mapping theorem. Open mapping theorem. Okay. So open mapping means which sends open sets onto open sets. So continuous means which pulls back open sets to open sets. Inverse image of open sets open. So first we do the following exercise here. Okay, let's see this. Suppose we have a Banach space say B, and so some particular vector is there, say by naught. Then we can define the translation mapping. So let this B be a Banach space. So again, normal linear space be okay, that's okay. Let's take Banach space. Let B be a Banach space. So B be a Banach space. And there is some vector say x naught in this Banach space. Now then show that this mapping phi from B to B defined by phi of x is equal to x minus x naught is a homeomorphism. Homeomorphism means it's bijective, continuous and open. Homeomorphism. So it's bijective, that's clear. It's 1 1. So if the images are equal, then the points are equal. And it's also on to, if you take any point on this side B in the codomain, then say x, then x plus x naught is the pre-image of that x. So this phi is bijective, that's trivial. Phi is bijective is trivial. This is trivial. Okay. Now if it's continuous, so continuous means usually you can use the sequential approach also here. Then inverse map is also continuous. So it's very simple. If you take any sequence in that domain in this Banach space B which converges to some point, then image of that sequence will converge to the image of the point. Apply the sequence approach because the continuity is equivalent to the sequential approach in any matrix space. Here we have a Banach space and every Banach space is a matrix space. So that's very simple technique. Or you can prove it in terms of open sets also, or in terms of can prove it also in terms of epsilon delta. But you can also do that. It's actually a translation operator. So it will preserve the distance. It is distance preserving mapping actually. So this is always going to be continuous, and inverse map is also continuous, because inverse map is also translation. So that's again also actually simple. Let's do this. So we have this. We have norm of phi of x1 minus phi of x2 is equal to, what's the norm of phi of x1 is x1 minus x0. Okay. Then minus times phi of x2 is x2 minus x0. So that's equal to norm of x1 minus x0. Okay. So that means it's actually isometric. This also phi inverse, अगर आप check करोगे, also this phi inverse, you can see this is phi inverse of x1 minus phi inverse x2. That's equal to norm of, this is going to be plus here, inverse map.
So is it there norm of x1 minus x0 or norm of x1 minus x2?
Oh, sorry, it's x2, right? It's x2 here. x2 minus x0 is there. And that's equal to norm of x1 minus x2. It's also symmetrical. Isometric. Okay. Yes. So both phi and phi inverse are continuous. So this implies both are continuous mappings actually. That means our phi is an homeomorphism. So therefore both phi and phi inverse, they are continuous. So therefore both phi and phi inverse are continuous, and hence phi is a homeomorphism. Next we prove the lemma, which is very important for open mapping theorem. Let's state this lemma for open mapping theorem. Okay. So the statement is, if we have two Banach spaces, if B and B prime are Banach spaces, are Banach spaces, these two are Banach spaces, okay, and if T is continuous linear transformation, okay, and if T between these two spaces, these two Banach spaces, is continuous and linear also. Linear transformation. Continuous and linear transformation of B on to B dash. So this also on to, okay, of B on to B prime. Then the image of each open sphere. Then the image of each open sphere, then the image of each open sphere, then the image of each open sphere centered on the origin, centered on the origin, centered on the origin, then the image of each open sphere centered on the origin, centered on the origin. So 1 minute please. Centered on the origin in B. So this is in B, open sphere, and its image now. Image of open sphere in B, which is centered on origin, contains an open sphere. This contains an open sphere. Contains an open sphere. Contains an open sphere. So this image, it contains an open sphere centered on the origin in B dash. Centered on the origin in B dash. Okay. So this is the lemma. So we have two Banach spaces, P, and this is B dash. Okay, this is our space B dash, and this is P. Okay, and this is the linear transformation. It's continuous and linear transformation. Then the image of each open sphere with center at origin. This is our open sphere with center at origin. This is say S. Suppose okay, S is the open sphere centered at origin. The image of this open sphere, तो इसकी जो इमेज होगी वो सपोज इस तरह की होगी, कोई इस स्फीयर की. This image of this sphere, it may not be sphere, image of sphere may not be sphere, but it's contained in some sphere with central origin. Okay, so this is the image of that sphere. This is TS. Okay,
सर शोर आ रहा है बहुत.
Actually ये लैपटॉप का है. So the statement is this: we have a given sphere, okay, on this codomain Banach space P, in this with center at origin. That's our sphere. Its image is some set. Say this one. This is its image, suppose. And the theorem says that this image of the sphere, it is contained in some sphere with center at origin, which is in B dash. Okay, that's the conclusion of this theorem. So given two Banach spaces B and B dash, T is the linear transformation which is also continuous between B and B dash onto map. It's onto map. Then the image of each open sphere, image of each sphere with centered at origin, is contained in some sphere with centered at origin in B dash. So proof of this theorem. So we have to apply here pair category theorem. So let's fix first the notation of sphere. क्योंकि आपके पास दो Banach space है, तो you have two types of spheres. So throughout this proof, we denote SR, the sphere in the Banach space B with radius R in origin and the center origin, and SR prime is the sphere in the Banach space B dash with centered origin and with origin as center and radius R. Okay, so let's fix those notations. So we denote by this SR and SR prime, SR and SR prime. They are the spheres, okay, the open spheres, the open open spheres. These are the open spheres with radius r centered on the origin, with radius r and centered on the origin in B and B prime respectively. Okay. So we have this SR, this is equal to R times S1. This is simple. SR is the sphere with centered origin and radius R, and S1 is the sphere, open sphere with centered origin and radius 1, but it's R times S1 actually. These two are equal. These two are equal. This is very simple, it is not too difficult. Now this T is linear, so this means that T of SR, which is equal to T of R S1, and that's equal to R times T of S1. So it means that actually we have to prove that image of each sphere with centered on origin is contained in some sphere with centered on the origin. So therefore it is suffice to prove the result for S1. हम S1 की इमेज पर कंसिडर, अगर हमने S1 के लिए प्रूव किया रिजल्ट, then it's true for each open sphere with any radius. S1 means the radius 1. So then we apply this one, and then we can also apply this, क्योंकि आपको conclusion भी देखना है तो वहाँ पर आपको image sets के लिए आपको देखना. But for image we have TSR is equal to R times TS1. So therefore therefore we prove the result. Therefore we prove the result for S1. हम S1 के लिए रिजल्ट प्रूव करेंगे, मतलब जो S1 जो स्फीयर है B1 में, जिसका सेंटर ओरिजिन है और रेडियस R है, will prove that image of this sphere is contained in some sphere with center origin in the Banach space of B prime. वो हम प्रूव करेंगे. तो इसके लिए हमें रिजल्ट प्रूव करना है. सो दैट मीन्स देयरफॉर वी हैव टू शो दैट, देयरफॉर वी शो दैट, देयरफॉर we show that T of S1, the image of this sphere, is contained in some sphere, is contained in some sphere means some SR prime in B dash. ये हमें प्रिसाइजली प्रूव करना है एक्चुअली दिस. So first we prove that the closure of this actually is contained in some SR dash. ये हम पहले प्रूव करेंगे, तो इसका फिर हम रिजल्ट इसका अप्लाई करके हम TS1 के लिए रिजल्ट प्रूव करेंगे. We first prove that okay, actually this is शायद I think this is what is the statement? Statement is this: we have to show that this sphere is contained. It's contained as an open sphere, not contained actually. It's here contained as an open sphere. So that it's like this actually. It's like this. The image. So this is the image. Okay, this is the image. This is the image set. It contains, okay, it's not contained in, it contains some open sphere. It's like this, this is the open sphere, this is your S dash, okay, see, S dash, not containing, okay. So image of every open sphere contains some open sphere in the range space B dash. So sorry for this, so we denote this. So बाकी it's rest of this it's right, so SR is equal to R to the SR, so we prove the result for this S1. So then we show that TS1 is contains, it is not contained in, okay, this statement says it contains, okay, TS1 contains, not contained, not contained, TS1 contains some SR dash in B. So we first prove that, तो अभी प्रूव करना कि TS1 कंटेन करा. So it's clear that this TS1 ये जो है ना, it is contained in TS1 closure, ये है आपके पास, because this is the set and this is its closure. Closure always contains a set. तो हम सबसे पहले क्या प्रूव करेंगे, हम प्रूव करेंगे ये जो TS1 closure it contains some sphere. एक्चुअली हमें प्रूव करना है कि ये sphere कर रहा है contain this one, मगर सबसे पहले हम प्रूव करेंगे this one always contains a sphere. फिर इसका यूज़ करके हम प्रूव करेंगे कि ये भी जो TS1 है ये भी स्फीयर को कंटेन कर रहा है, ओके. सो लेट्स फर्स्ट प्रूव दैट दिस first we prove that TS1 closure, okay, contains TS1 closure, this one it contains some SR prime, okay, in B dash, okay, obviously in B dash. Now this T is on to, since T is on to, it's given to be on to, since T is on to, so therefore we must have this, the Banach space B dash is union of spheres SR, not TSR, sorry, TSN, it's TSN, not TSR, TSN, n runs from 1 to infinity, okay. So because your T is on to, so so this is always true. You can prove it, one inclusion is trivial, that union is always contained in B dash, because ETHSN, T of Sn, image of Sn or T is contained in B dash. So since so let's prove this star, okay, let's prove star, since T of Sn it's always contained in B dash for all n greater or equal to 1. So this means union of TSN is n runs from 1 to, that's simple है. This one is contained in B dash. आपको एक्चुअली कन्वर्स प्रूव करना है. कन्वर्स के लिए आपको ऑन टू का यूज़ करना है, क्योंकि आपने बता दिया यहाँ पर सिंस टी इज ऑन टू, देयरफॉर दिस बी डैश इज इक्वल टू दिस, इसकी ऑन टू प्रॉपर्टी का यूज़ हो रहा है. So let's prove the reverse inclusion. So assume that let's take any point y in B prime. So we have to apply the ontoness. So then there exists some x in B such that T of x is equal to y. So this x must be the center of some sphere. Now let's choose. So then this x this X belongs to Sn X, and which is contained in obviously in B. Okay. So this means Sn x minus x. Okay. Sn x minus x. So I want to prove this this y. This should be in. So that y should be in some Tsn. Okay. Okay. So this is the Banach space B here. So X is here. So I can choose n so large. Say this is say our origin, suppose. So I can choose n so large such that this sphere it contains X. So okay, because this is origin here. So I can choose n large such that the sphere with center origin and radius n. So अब कितना ही बड़ा n लो, जो sphere होगा ना S0n, it will always contained in the Banach space B. So let's write here this. Actually, this as it contains in Sn for some n. What's the reason? So you can write here this. Then the norm of X is less or equal to n for some n. For some n greater or equal to 1. Because actually every real number, every non-negative real number is dominated by some natural number. So we can apply that result. That's called Archimedean property that you can apply here. So so whenever norm of X is less or equal to n, that means X belongs to this Sn. X do not subset. Sorry, it's X belongs to this. X belongs to Sn. So Sn is the sphere, open sphere with center origin and radius n. Right. So this means T of X, it belongs to T of Sn. What's T of X? For some n. Okay. For some n greater or equal to 1. So which means Y belongs to T of Sn. For some n. Okay. So that means this P prime is subset of union of T of Sn and runs from 1 to infinity because it is in one of this T of Sn. This Y. Okay. So that means B is equal to B prime is equal to union T of Sn and runs from 1 to infinity. Now this B prime, it's a Banach space. So it cannot be written as a countable union of no identity sets, and here it's countable union of sets, union of these sets Tsn, because they are countable in number. It's Ts1, Ts2, Ts3, so they are countably many sets, and B dash is union of such sets. So that means at least one of them is not Nova dense. Because if each of them is Nova dense, then you have expressed B dash. Then you have expressed this B dash as a union of Nova dense sets, which is not the case because we cannot do that for Banach space. The Banach space cannot be written as countable union of Nova dense sets. So that means at least one of the set is not Nova dense sets. So there exists n naught greater or equal to 1 such that T S n naught is not nowhere dense. Nowhere. So nowhere dense का मतलब क्या है? इसका जो क्लोजर है उसका इंटीरियर जो है दैट्स एम्प्टी. नाउ दिस इज नॉट nowhere dense. तो इसका मतलब है कि the interior of the closure of this set is non-empty. So that means interior of TSN not closure is non-empty. इसमें हम कोई ना कोई पॉइंट चूज कर सकते हैं इस सेट में. Okay, so let's choose point Z naught. So choose a point Z naught which is in the interior of T of Sn naught closure. But I want to choose a point, say point Y naught, which is in interior as well as in Tsn naught. So claim is like this. Claim there exists Y naught in B such that this Y naught, it belongs to the interior of T of Sn naught closure, and it also belongs to T of Sn naught. तो मैं ऐसा वाई नॉट चूज करूंगा जो एक तो इसमें हो. Z नॉट तो है इसमें, बट सपोज Z नॉट अगर इसमें ना हो, इसमें इट्स नॉट हियर द क्लोजर के, इट्स नॉट क्लोजर, इसमें तो होगा ये दिस. I want to choose a point Y naught which is also in this interior of TSN not closure, but that point is also in TSN not. TSN naught. Okay, Z naught is in the closure. I want to find the point Y naught which is in TS naught and also is in the interior of TSN naught closure. So let's see how this happens. This one. So Z naught, let's do it in the next page. Okay, so we have this. Z naught is in interior of T Sn naught closure. It's like this. So interior, it's in the interior. Interior means I can find or positive. So this is our set. This is our set T Sn naught closure. Okay, closure of this. And Z naught is in the interior. This is Z naught, so I can find some sphere. This is the sphere with radius r. Okay, radius r. This is the sphere with center at Z naught. Okay, that's the point Z naught. Okay, Z naught belongs to this set. This set is sphere with center at Z naught and radius r. And I want to choose the point